So welcome afternoon session, 6 o'clock, review of Lab 4, which was focused on electrical properties of materials. So the review is going to be really short because the lab itself was very short, and it's actually not much to talk about because based on submissions, based on the reports, it looks like everyone done really well. Again, we haven't marked yet Lab 4, but preliminary results are actually quite encouraging. So I think the mark for Lab 4 is going to be skewed well above average. Okay, let's sort of brush over what we had. So we had 8 materials which were placed on the deck. There were only 2 insulators. They showed overload on the multimeter, and 6 other materials from top to bottom. The black wire or the rusty wire, for example, at Nathan, was mild steel. Then it followed with stainless steel. Then there was copper, there was brass, then there was aluminium, a really soft and bendy type of a wire. Then the highest resistance material was nichrome, and after nichrome we had either green or red sample. That was PLA polymer, 3D printed one, and the bottom sample that was transparent one was nylon. Just it was a very thick, large gauge fishing wire. So majority of students could identify it really well. So you had 2 criteria to base your arguments and judgments on. The first criteria was actually visual and tactile. Another one was using electrical measurements such as resistance. And in order to get, resistivity. And in order to get resistivity, you needed to find out what the resistance of the samples were, of these wires were initially in unpowered assays measurement, for which you needed to consider geometrical size of the sample, such as cross-sectional area and the diameter. If you were careful with units, and majority of students were really careful with units, you actually got reasonably good results. So those classes that I have monitored personally, such as those labs at Nathan and also the Thursday class, pretty much myself and either Jatinder or Kathy were screening through your inputs into the tables, and we could identify if there were errors and actually inform students of any errors that needed to be corrected. Overall, if you were taking measurements in unpowered setup and powered setup, your value for resistance R that trails from the Ohm's law will be almost identical. In unpowered setup, your resistance measurements were a bit grainy. There were quite a lot of error in the numbers, which was perfectly fine. With powered setup, you would get higher fidelity or higher resolution on resistance, and consequently resistivity values were also obtained with a much better precision and accuracy. So overall, what we saw from your reports and my feedback is that you've done really well. The measurements were straightforward, instructions were followed to the T, and you got reasonably good data. Some differentiation existed in ranking materials based on the cathodic versus anodic behavior. Okay, so you had 8 samples. Across these 8 samples, so if you would look back at the back of your instruction manuals, there were 2 tables. So you could identify, one table was for resistivity, another table was for galvanic character, either plus noble materials or minus highly anodic. So out of your samples, the cathodic materials, these are inert noble materials, those that will not corrode, would be starting with insulators, such as your polymers. They generally would not participate in any chemical reactions. And then from your samples, so when you would consider your samples, your metallic samples, from aluminium that would sit at the bottom, this is the most anodic material. So remember, I'll just maybe give a little bit of a revision about anodes and cathodes. So you have galvanic coupling, a metal that sits below and donates electrons to the metal that sits above is an anode. Anode below cathode on galvanic series table, it donates electrons to the noble metal. That generally metal that sits above is an acceptor. So it basically takes electrons in and remains unaffected in chemical reactions or in galvanic reactions. The one that actually gives electrons is, pardon my colloquialism, metals die when they give the electrons to someone. For metals, electrons is life, okay? So if a metal is willingly or unwillingly gives away its electrons, it's self-destroying, right? So an atom basically is disintegrating because the outer shell, the outer layer that keeps atom intact, these are the electron clouds, they've been depleted. So an element that is giving electrons is an anode, it is oxidizing. And the metal that accepts electron is being reduced. And being reduced is a term which is used to signify that now, well, that metal perhaps been in some chemical state, it's been reduced to the basic state. It's no longer oxidized. So it's a bit of a misnomer, like in chemistry. So the noble metal is being reduced to its original state, while the element that oxidizing is being oxidized, and it's also donating electrons. So from the metals that you had, the most anodic one would be aluminium. And generally, if you think about aluminium structures, they're very easily oxidized. The coating, the white, fluffy, powderish type of coating is aluminium oxide, which is formed in aluminium. The most inert materials that we had across the metals in the wires that we had on the deck was stainless steel. Okay, so stainless steel will be the top dog, right? It will be the most cathodic, the most noble metal across all other metals. So what I have advised for students in the labs which I've administered and run is that basically identify the low dog, the bottom dog, and the top dog. Okay, the top dog would be in metal stainless steel. The lower dog is going to be aluminium. And non-metallic samples will be polymers sitting above stainless steel. All the rest of metals, they're going to be in between, okay? You can grade them as medium to low cathodic or medium to low anodic. It's up to you. But it was important to identify the most anodic and the most cathodic one, okay? That way, this is where the most marks are going to be focused on. And so far, what I've seen, and I've only seen about 15 to less than 20 reports, it was sort of a hit and miss. So half of them were okay, half of them were a bit on the error side. Again, this cathodic anodic conductor ranking question only carried 1 point or 1 mark. So if you got it only half right, not a big deal. You may lose half a point, okay? With the constructive answer questions, so you had 3. Let me read them out. In the first question, the question asked, define electrical resistivity and conductivity. Explain whether the percentage difference calculated in task 2, that was the difference between powered and unpowered resistivity values, reflects on intrinsic material behavior. If not, explain the likely experimental causes. Okay, you don't need to write a lot, so I was only expecting, 3 to 5 sentences maximum. So when you discuss resistivity and conductivity, they're reciprocal of each other. Both of them highlight intrinsic material property. Okay, so what you need to be mindful about is that the Ohm's law applies, such as V equals IR, applies to the systems, to the circuits. So electrical circuits, they have different elements. We can have a battery, we can have a power source, we can have a lamp, we can have a resistor, we can have ammeter, we can have voltmeter, etc. All these are elements within the electrical circuit. So the Ohm's law applies at the macroscopic level. So it takes into consideration resistance of the circuit, all the elements connected. All these individual elements are made out of something. Okay, the wires are made of copper, resistor is made of something else, and different materials have their own inert, intrinsic, physical, philosophical properties. Okay, so we can have copper displaying only copper-like conductivity or resistivity. Stainless steel, we have its own intrinsic value for conductivity or resistivity. All elements will have the intrinsic values. Okay, they are separate from the electrical circuit. Intrinsic value means that the material interacts with electromagnetic field on the basis of its atomic structure, bonding, and defects. So when we define it as an intrinsic property of the material. One, if it's resistivity, it's how material intrinsically opposes the current flow, or you can write it in a more sophisticated way, induced electromagnetic field, or conductivity, how material intrinsically conducts the current. This is it's an acceptable explanation, and it's a sort of a bit of a flat Earth explanation, or allows electromagnetic field to effectively interact with the material structure, if you want to have more sophisticated way to explain it. The percentage difference in resistivities obtained in unpowered and powered setups, they do not correspond to intrinsic material property. Okay, they're really indicative of the tools that we were using. So in an unpowered setup, we used crude tools. Okay, the multimeter was low power tool with its own low fidelity measurement scale, and it could not simply push the current through adequately through our resistors. So we got really low fidelity measurements. In the powered setup, we could use a powered source that could push the current through the wire and magnify the resistance signal so we can read it better and use higher resolution and higher significant numbers. So no, it's not related to, so the percentage difference is related to the instruments and the tools and the resources that were used to probe materials' intrinsic property, but not relates to an intrinsic property of the material per se. And that's it. So, and likely experimental causes, simply not having enough current, for example, in unpowered setup, not accounting for resistance in the wires, not accounting for the probe contact. You know, a thinner, for example, if I have a contact which is thick, right, my contact will be much more sensitive if I'm probing something and passing current through it. However, if I take a really tiny needle, my current isn't going to be very high when probing conductivity in my resistor or in my conductor. Okay, so the cross-sectional area of the probes, also the setup that we used was instructional, adequate enough, but it wasn't a research base. Okay, this is how I would address question 1. If you've done even 1/3 of my explanation, so we're able to sort of address it to 1/3, that will be viewed really positively. So what would be percentage difference? So depending on materials, what we noticed, excluding the insulators, such as those polymers, and again, with the polymers, honestly, I've just mentioned to students, don't worry about which one is which. You know, if you could identify transparent polymer as nylon, it's great, it's efficient wire. But another polymer, whether it's red or green or whatever, it could be anything, but it was a polymer. Okay, the percentage difference we noticed, like when I was screening through students' answers, they were anywhere between 10%, this is the best scenario, to about 80, okay? Sometimes close to 100, but not an order of magnitude. So it was sort of a bit of a low value float. In some measurements, I saw a variation between about 10 to 40, and that's the best. Others I've seen anywhere between about 15 to maybe 100. That's sort of a ballpark value. Again, something that I will be really mindful about. So again, this observation only concerns Wednesday Gold Coast group. I was very careful designing these kits, and at Nathan, I made sure that the top wire, which was mild steel, was skinned using sandpaper, and it actually provided sufficient current flow. When we were running first tests on Thursday, I noticed that the design of the wire on the Gold Coast, which I could not monitor, had an insulator coating on top. And that insulator coating could trigger significant resistance in that black wire of as a mild steel. It was like 12 ohm, 16 ohm, and it was also floating. I immediately corrected and asked the technical staff. Yes, yeah, it looked like it had paint on it. That's right, Joshua. So I immediately corrected the kits. So I've asked the tech member, Red, on the Gold Coast to remove the wires and skin them and abrade them using the sandpaper to remove the plastic polymer finish on the surface. And then when they were put back, the resistance was less, or it sort of was comparable to stainless steel, which was correct, okay? So mild steel was slightly more conductive, less resistant than stainless steel. So if you had that wire and if you were on Wednesday class on Gold Coast, there will be significant leniency applied to you because the kit, and especially one wire, was compromised, okay? It was just a bit of an error from the setup. Again, you're not going to be penalized. It's okay. Even if you have not identified that wire, it's perfectly fine, okay? Yes, it was, I didn't know, and you see my TAs, sorry, I shouldn't say my TAs, sessional staff didn't tell me that. I was quite disappointed when I saw it in the first class on Thursday when I was teaching on the Gold Coast. And no one told me. So to me, it was just a bit of a glaring error that no one could pick it up. But I will instruct the sessional staff to apply sufficient leniency mark in those Wednesday classes, because you had really bad distractor, and it was unjustified distractor, honestly, because it was just bad, okay, and acknowledge it. Okay, let's move to question 2, constructive answer question. When aluminium and stainless steel are coupled in saline environment, saline means just salt water, identify anodic material and explain the mechanism driving corrosion. Propose 2 design strategies and justify how each interrupts the electrochemical process. I think I've written it at night, and maybe it's a little bit convoluted question. Okay, so what it actually means, like in plain flat earth terms. You have 2 materials, aluminium and stainless steel. They are sitting in salt water. What would you do to stop corrosion? Okay, that's a simple question. Okay, the way I address it and the way I've recommended students at Nathan and Gold Coast Thursday session to address it is that, okay, identify, first, number 1, identify materials which are going to be anodic and which are going to be cathodic. Okay, aluminium sits below you, it's a bottom dog, it corrodes, it oxidizes, it sends electrons to stainless steel. Stainless steel is a noble material in that coupling, and no matter if it's active stainless steel or it's a passive stainless steel, it's still a noble metal in the coupling. It will not corrode. Aluminium will corrode. What can you do to stop corrosion? Well, paint it, smear it in grease, run in so-called impressed current in the opposite way. So because we have aluminium at the bottom and we have stainless steel at the top, electrons go from aluminium to stainless steel. So one of the solutions that we discussed in the lecture, how to stop corrosion, well, there were actually about 6 solutions, but you're only required to provide 2. Paint it, okay? So stop the electrons loss from aluminium. Then, because electrons go from aluminium to stainless steel, you can actually run an inverse current. It's called impressed current from stainless steel down to aluminium in the same magnitude as aluminium will give electrons to stainless steel, stopping electrons flow. It's called an impressed current or DC current that will stop the corrosion. You can polish the surface. So if you polish aluminium surface and you polish a stainless steel surface, there'll be no peaks and valleys. And where there are peaks and valleys, there are differences in electronegativity on metals. They will act as galvanic individual sites. So by polishing materials, we can actually stop the localized corrosion, especially like pitting. Then protect the overall structure. So, we can just simply use, encase it in something. It's the same as, smearing it in grease or painting it, but you can block it, block these materials from even being immersed in salt water. You can also lower the temperature if you can. So freezing is a good idea. So because if you remember, I think it's called Nernst equation. In the Nernst equation, you've got variables such as metals and their galvanic values, and also the temperature and the number of electrons, right? So lowering the temperature works. So freeze the environment, freeze the system. These are far too many options, but if you could think about 2 out of those, that will be great. Okay, question 3. A conductor must operate in a saline elevated temperature environment, so hot water, salty. Select the most suitable material from your tested wires and justify your choice by considering electrical performance, such as resistivity, stability, and corrosion behavior, electrochemical potential, and passivation. So the most conductive material you had were copper and brass. The least conductive was nichrome and stainless steel, or maybe mild steel with a coating on top. Okay, so think about that you need to run a naked wire in the hot, salty bath. What would you use? Okay, I mean, everything will corrode. It's a bad environment for materials. It's a really bad environment for metals. That electrolyte will eat away any metal, apart from maybe gold and platinum. It's really aggressive environment. So, but what would you use? So out of those metals, I would personally choose not brass for bronze. I think we had bronze, right? Not brass. So bronze has copper and zinc. It's an alloy of a good conductor, such as copper, and a really bad galvanic anodic material, such as zinc. Zinc will oxidize and will compromise brass. Okay, so brass, despite the fact that it can be a good conductor, is not suitable simply because it has zinc. Copper is suitable short term. If you write down copper short term is great because copper will oxidize, so it will become green and ugly and slimy, but nonetheless, it will conduct current suitably. Another option, if you would prefer preservation of a material structure instead of improved conductivity, use stainless steel. Stainless steel will survive salty, hot environment, but it is not a great conductor. Okay, if you really want to preserve the material and don't care about conductivity, use nichrome. So nichrome, it's really sorry, not nichrome, use stainless steel in the environment which is hot and salty. Stainless steel will immediately become passive. So there were two flavors to stainless steel that we had listed on the table. Remember, materials, when they are in unoxidized state, in fresh state, they are active. They are willing to participate in oxidation reaction. As soon as they form an oxide, they immediately become passive. So stainless steel, no matter if it's active, it will become passive, but it's a better solution. Nichrome will corrode slightly worse than aluminium, but best solutions, copper and stainless. Okay, let's look at multiple choice questions. Okay, I'll read out all the questions. So how does temperature affect electrical conductivity in metals? Option A, conductivity increases due to increased electron mobility. No. Option B, conductivity decreases. Okay, wait. So how does temperature affect electrical conductivity in metals? So let us just simply recall, before I read out all the questions, let us recall what we know about metals. Okay, so scientists, they cool electrical components, right? So mobile phone works well when it's cool. Batteries, not really. I mean, they starting electrical cars in cold, it's another problem. But generally, when materials are electrical circuits, electrical materials, electrical systems become hot, they start to lag because resistance increases, right? So what happens is that we heat up a conductor, electrons get more energy, and they start jumping around, and they move around in an erratic pattern, and they also beat themselves across the lattices that generally most metals have, okay? Also, heat is detrimental to semiconductors. So where we have p and n junctions, they like to have the electrical gates either closed or open. They don't like noise, and this noise is created through heat. So the physical phenomena is against temperature. The higher the temperature, the worse the conductivity is. And therefore, when, for example, physicists run the experiments, or you look at space science, or you look at colliders, or you look at particle accelerators, a lot of equipment is cold, right? When you look at space shuttles that are sitting on the launching pads, there are steam clouds around them, okay? This steam is actually liquid nitrogen cooling down electrical components. So in order to function well, because when the space rocket, for example, takes off and goes through the atmosphere, it heats up. And it's better to have components really cool so they function through that process of a rocket abstracting from the Earth and going through the really aggressive friction-prone environment of the atmosphere. Okay, so fundamentally, heat is bad for metals. Let me reiterate the question then with the knowledge that we know. Question 4, how does temperature affect electrical conductivity in metals? Option A, conductivity increases due to increased electron mobility. Well, electron mobility increases, but conductivity is reduced. Bad answer. Option B, conductivity decreases due to increased electron scattering from lattice vibrations. Option C, conductivity is unaffected by temperature. Wrong. Option D, conductivity increases as electron drift velocity is reduced. No, option B is correct, okay, from those options. Question 5, what most contributes to metal corrosion in aqueous environments? Okay, let us review this question. So corrosion, what really corrosion is? So this is when metal is donating its electrons and becoming oxidized. And corrosion is facilitated by aggressive electrolytes, high temperature, and the high electrical potential between an anode and cathode. Okay, so this is our basic knowledge. Let me read the options. Option A, uniform atomic structure of anode. No. Option B, electron transfer between anodic and cathodic sites via an electrolyte. Yes, this is the correct option. Option C, decreased temperature of electrolyte. No. Decreased temperature actually lowers the reaction. And option D, absence of dissolved oxygen. Well, yes, but again, anodic material will corrode just due to their nature. Oxygen is there to oxidize anodes, but most contributions would be electron transfer. That has to happen between anode and cathode. Okay, question 6. In galvanic corrosion of two dissimilar metals in contact with electrolyte, which metal corrodes? Option A, more noble metal corrodes. Wrong. Noble metal is a top dog. It doesn't. Okay. Option B, less noble metal corrodes due to lower electrode potential. Yes, this is correct. Less noble means anodic, and low electrode potential, yes, it's anode. It will donate electrons. C, both corrode equally, can't happen. Option D, corrosion is prevented by electrical contact. No, that's wrong. That's nonsense. Okay, so all questions, multiple choice questions, had B as correct answer. And that's it for today. So yeah, about 30 minutes for the review. We are slightly lagging behind the markings of Lab 3 and Lab 4. But again, we'll mark them within the next 2 weeks. So we hope to conclude Lab 3, which I have on my table. And hopefully this week we'll finish Lab 3, and Lab 4 we'll hope to finish next week by Friday. Okay, and that's it for today. There are only 7 of you remaining out of 390 something. Okay, anyway, the session is recorded. Hopefully it was useful. Hopefully you can enjoy the rest of your day. Any questions, guys? Anything? No? Okay, let me turn off the recording then.